Hello viewers. In this presentation, we are going to talk about transfer of heat. Heat may be transferred from one point or a body to another in three different ways. These are conduction, convection, and radiation. In conduction, heat flows from one hot end to the cold end of the same solid object without there being any net movement of the particles of the object. In convection, heat is transmitted through a substance from one point to another due to the actual bodily movement of the heated particles of the substance. In radiation, heat is transferred from one place to another in a straight line with the speed of light without heating the intervening medium. Thermal conductivity of a solid is a measure of the ability of the solid to conduct heat through it. Under steady state condition, the temperature at points within the rod decreases uniformly with distance from the hot end to the cold end. The fall of temperature with distance between the ends of the rod in the direction of flow of heat is termed as temperature gradient. That is, theta g equal to theta 1 minus theta 2 by x, where theta 1 denotes the temperature of hot end, theta 2 denotes the temperature of cold end, and x is the distance of separation between the hot and cold ends. Experiments show that under steady state condition, the quantity of heat Q that flows from the hot end to the cold end is directly proportional to the cross-sectional area, is directly proportional to the temperature gradient, and the time for which heat flows. Combining these conditions, we can say Q is directly proportional to A times theta 1 minus theta 2 times T by X. Here, we introduce a proportionality constant termed as coefficient of thermal conductivity, and rearranging the above equation, it can be expressed as K equal to Qx by A times theta 1 minus theta 2 times T. Similar to electrical resistance, the concept of thermal resistance can be thought of. It is the opposition of a body to the flow of heat through it. It is represented as R equal to L by Ka. Now, thermal radiation is the radiant energy emitted by a body solely on account of its temperature. Thermal radiation, like light, is electromagnetic radiation. It has all the general properties of electromagnetic wave. Thermal radiation can travel through vacuum, travels in a straight line, obeys the laws of reflection, can be refracted, moves with the speed of light, does not heat the medium through which it passes. Thermal radiation obeys inverse square law. They also exhibit the phenomena of interference, diffraction, and polarization. When thermal energy falls on any surface, a part of it is absorbed, a part of it is reflected, and rest is transmitted. That is, R plus A plus T equal to Q. We can rearrange this equation and rewrite small ra plus small a plus small t is equal to 1. Here small r is the reflectance, a is the absorptance, and t is the transmittance of the substance. The above expression clearly indicates good absorbers of heat are bad reflectors and vice versa. A perfectly black body is the one which absorbs completely all the radiation falling on it. Here we have demonstrated the design and functionality of Fairy's black body. Any radiation entering the hole is reflected many a times at the inner walls of the sphere. After a few reflections, almost entire radiation is absorbed. Point to be noted, in this design, not the entire object can be considered as black body. It is just the hole which acts as black body. Now, few terms we need to know before moving further into blackbody radiation. These are monochromatic emissive power. The monochromatic emissive power of a body at a given temperature and for a given wavelength lambda is defined as the radiant energy of that wavelength emitted per second per unit area of its surface within unit wavelength interval around lambda, that is between lambda plus minus half. Next, we have emissive power. The emissive power of a body at a particular temperature is the total energy of all wavelength radiated per second per unit area of the body. Since the range of emitted wavelength can be anything, mathematically emissive power is represented as small e equal to integration 0 to infinity E lambda d lambda. Now, emissivity. The emissivity of a body is the ratio of the emissive power of the body to the emissive power of the perfectly black body at the same temperature. Mathematically, it is represented as epsilon equal to small e by capital E, where capital E is the emissive power of a perfectly black body. Next term is monochromatic absorptive power. The monochromatic absorptive power of a body for a given wavelength lambda is defined as the ratio of the thermal energy absorbed by it in a given time to the total energy incident on it for the same time both in the unit interval of wavelength range around lambda, that is lambda plus minus half. The following figure shows the way in which energy is radiated by a black body with its distribution in various wavelengths at different temperatures. The figure clears the following points. The total energy emitted by a black body increases rapidly with increase in temperature for any wavelength. At a given temperature, with increase in wavelength, the energy E lambda first increases, reaches a maximum and then decreases, which means for a given temperature, the radiant energy is maximum for a particular wavelength, here denoted by lambda m. As the temperature of the body increases, the peak of the curve shifts towards shorter wavelength. The area enclosed by a particular curve represents the total radiant energy of all wavelengths per second per unit area emitted by the black body at that temperature. Based on the nature of black body radiation, various laws were established. Wien's displacement law. This law states that the product of the wavelength at which maximum energy is emitted and the absolute temperature of the black body is always constant. That is, lambda m times T is constant. Next we have Stephen's law. This law states that the rate at which a body radiates energy, that is energy radiated per second, is directly proportional to the fourth power of the absolute temperature of the body. That is, P is directly proportional to T to the power 4, which can be written equal to epsilon sigma A T to the power 4. Here, epsilon is the emissivity, sigma is Stephen-Boltzmann's constant, A is the surface area of the body. Next we have Kirchhoff's law. According to Kirchhoff's law, the ratio of the emissive power to the absorptive power for radiation of a given wavelength is the same for all bodies at the same temperature and is equal to the emissive power of a perfectly black body at that temperature corresponding to same wavelength. That is, E lambda by A lambda is equal to E lambda. Newton's law of cooling applies when a body is cooling under condition of natural convection and the temperature difference between the body and the surrounding is small. This law states that under condition of natural convection, the rate of cooling is directly proportional to the temperature difference between the body and the surrounding, provided the temperature difference is small, that is less than 30 degrees Celsius. Therefore, rate of cooling is directly proportional to theta minus theta 0. The Sun is the central body of the solar system. The two important parameters are solar constant and solar luminosity. Solar constant is the amount of energy received from the Sun per second per unit area by a perfectly black body placed on Earth, the area being perpendicular to the direction of radiation. Its value is 1.388 times 10 to the power 3 watt per meter square. Solar luminosity is the amount of energy emitted by the sun per second in all directions. Its value is 3.9 times 10 to the power 26 watt. To summarize, in this presentation we have discussed the fundamentals of heat transfer, the processes of various heat transfers, and various laws such as Wien's displacement law, Stephen's law, Kirchhoff's law, Newton's law of cooling.